Hello everyone, welcome to today's session. Today we will discuss about very important topic related to electromagnetic fields and transmission lines. Today we will try to relate the circuit elements and the field elements. So the topic of today is continuity equation and Poisson's and Laplace equation. So let us begin with the continuity equation. As name suggests, it gives continuity of the charges with respect to various parameters. So say this is our topic, continuity equation. So we have to derive the continuity equation. We will begin this topic with the very basic definition of current. Current is defined as the charge per time. How many charges are flowing in given time? That is nothing but current. Current is flow of charges. Normally we consider the flow of electrons. Those are negatively charged particles. So current I is defined as I is equal to negative of dq by dt. Let us consider it as our equation number 1. Now we have to relate these currents with other parameters. Now current is a circuit parameter. Along with that we will also see the current density parameters. What is current density definition? Current density or any kind of density is defined as the cos per area. Say J is current density here. It is the density created by current, say some differential current dI per some differential surface area ds. So from here we can say that dI is equal to J bar dot ds bar. If we want to find out the whole current I from here, we have to take integral of right hand side, that is integral of J bar dot ds bar. Say this is expression number 2. Now what we have to observe here? The current I is a scalar quantity. All of us know that current I is a scalar quantity. Few of us may not know about it. One may think that current is having direction as well as magnitude. Then how it is a scalar quantity? By definition of vector, any object, any parameter who is having magnitude and direction should be considered as vector. But here current is having magnitude given in amperes, it is having direction, it flows from one terminal to another terminal. Still we consider it as a scalar because it doesn't follow the rules of vector addition. That's why current is a scalar quantity. One more thing, if we consider a current carrying conductor, and if there is a differential length, say dl, and if we take the product of current flowing across this differential length dl is a vector, then this product is not a scalar quantity. This product is a vector quantity. Right. I hope you will remember this. So this is second expression for current I is equal to J dot ds. Now we will explore it in more detailed way. What is current? Current is a flow of charges. And what is current density? It is also flow of current. Now if we take another definition of current density in terms of volume charge which is present in some place. So if we consider that there are charges present everywhere in a volume. Now if they are static charges, that means they are not constituting current. But if this complete box of charges moves in some direction, then it is nothing but flow of current, and if there are multiple current, that density is j. How they are all related with each other? So let us consider some density of charges for this volume. What we will call it? We will call it as, say, rho v. So say rho v is the volume charge density. So any density, as we have discussed earlier, can be given by a simple relation that rho v is equal to the cos of charge density is nothing but charge, say some dq, differential charge present in this differential volume, and inversely proportional to its volume, say it is dv. So from this what we can say, what will be the dq equal to? From here we can say dq will be equal to, this term will go to LHS, so we will get dq is equal to rho v dv. So if we want to find out the overall charges present here, then what we have to do? We have to take integration of the RHS side. So q will be equal to integration of rho v dv. Say this is our expression number 3. Now what we have to remember here, this expression for current is equal to integral of j bar dot ds bar. This is surface integral, and here we have integral of rho v dv. This one is volume integral. So what is the difference between them? Surface integral and volume integral are double and triple integrals. Now if you see this ds bar is nothing but a surface. Surface means double integration for two sides. There will be two axes. So this one we can also write as, I is equal to double integral of j bar dot ds bar, right? So this one we can consider here. Okay, so this is about q and v. Now let us keep the value of charge q from equation number 3 to equation number 1. In equation number RHS we have one q. So what we can write here, say I is equal to, in place of q what we have to write, d by dt. So here we will get integration of rho v dv. So this is our new value of current. Now let us call it as, say, expression number 4. Now if we observe, we have two expressions here. I is equal to integral of j bar dot ds bar, and again I is equal to minus d by dt rho v dot dv. So we can equate both the currents. So let us equate them. Let us see what happens when we equate them. So we can write here, say, minus d by minus d by dt into integral of rho v dv can be written as equal to integral of, say, j bar dot ds bar. Now say this is expression number 5. Now here if you observe, these two terms are having different kind of integration. Here we have triple integration. Here we have double integration. So what we have to do? We have to equate them. Before that, equating them, we have to remember the theorems. We have discussed about two theorems. They use as del operator. What is del operator? Del operator is a vector spatial operator used to define the terms in space. So say del Let us consider del operator, which represent the terms in space. So del operator, how del operator is given as? Del operator is given by, it is in 3 dimensions. In 3 dimensions, if we consider 3 axes, so in 3 axes we may have, say, z, y and x. Then del operator for Cartesian coordinate system will be given by dou x it will be set dou x into ax cap plus dou y into ay cap plus dou z into az cap. Now this del operator can be used with dot product or cross product. So let us see what we get when we take dot product or cross product of this del operator. If we take del operator dot product with any vector, then we call it as a del dot any vector is called as divergence. We will discuss what is divergence also. And if we take del cross any vector, then it is called as curl. Divergence is outflow or inflow of the forces, and curl is the circulation of the forces. Now for example, if we see example of some water filled balloon, then here you can see we can see some water filled balloon GIF. If someone puncture it, what is happening? The water flow is going outward in all the direction, and where the volume of this balloon is going, it is shrinking toward the zero. So this is one example of divergence, the forces going all around outside and the volume is shrinking towards zero. Another example of divergence is the puncture of tube. Any vehicle, tube, cycle, bike or car, if suddenly it gets puncture or blast, the air force will go in all the direction and the volume of that tire tube will shrink toward the zero. So here we are mainly related with del dot vector, the dot product. We have to use dot product. This dot product is useful to convert the integration. Our problem is that one side is triple integration and another side is double integration. So what we can do? We can convert them by using one theorem. That theorem is called as the theorem is called as divergence theorem. So what we can do by using divergence theorem? By using divergence theorem, we can convert this double integral into triple integral. There is a simple rule for this. We use dot product. If we consider a vector, suppose our vector is j bar dot ds bar. So for this, what we will write? Say we have surface integral double j bar dot ds bar. So if we apply divergence theorem on this, what we will get? We will get triple integration, that is volume integration, but we have to take product of j bar with del dot product. So here we will write del dot j, that is divergence of j, and this ds will be converted to volume integral, say that is dv. So by this way, by using the divergence theorem, what we are doing? We are converting the surface integral into volume integral. Now we can keep this value in equation number 5. So we will get LHS and RHS, both the sides, as volume integral. So let us keep these values. So what we will get, the new values we will get here as, so we will take equation 5. LHS we have dou by dt into triple integral we can write for volume, that is rho v dv. Now RHS also we can write in the form of triple integration, but this time we have the divergence of current density del dot J. Now it is also volume integral. Now if we equate these two equations, so what we can do in these two equations, say let us cancel out this volume, this triple integral. What terms will be remaining? The remaining term will be, say, minus d rho v by dou t is equal to del dot J. This is nothing but continuity equation. Now if you observe this expression is nothing but the divergence of current density going in all the direction, which is directly related with the volume charge density present in that volume in given time. It is nothing but the expression of current also. Current is charge per time. Here the divergence of current density is nothing but charge density per time. It is the same example of balloon. What he is saying, del dot, what it is trying to say is that del dot J is equal to del dot J, say here is del dot J, divergence of the charges. Let us consider this water as the charges. How much it will go outside? The available charge density, water density inside that volume is nothing but equal to the current density. So it is dou rho v. In how much time they are going out? That is dou t. So this is nothing but continuity equation. So let us now check out for the Poisson's and Laplace equation. Okay, now let us discuss about Poisson's and Laplace equations. These are also very simple and interesting equations based on the same concept of divergence. So let us move it aside and let us begin our topic, that is Poisson's equation and Laplace equation. So first we will see Poisson's equation, and the Laplace equation we will get by default with it. Let's say Poisson's equation. It has nothing to do with the snake poison or the harmful poison. It is named after the scientist who derived this expression. His name was Simon Dennis Poison. So based on his name, this equation is based. So this is also related with the divergence, say del dot D is equal to rho v from the Gauss law. What is this expression? Same example of balloon we can consider to understand this concept. What it says the divergence of D. What is D? Electric flux density. If electric flux density is filled in some volume, then its divergence, say del dot D, how much divergence will be there? How much flux will go outside? Flux is created by the charges itself. Gauss law says that the flux psi is equal to nothing but charge. We can see in the example of capacitors, there is dielectric between them, but we get transfer of charges from one plate to another plate, but not in the form of electrons. They do not jump in dielectric. They run, they jump, they move in some other form. That something is called as flux. That flux is nothing but equal to the charge creating it. So del dot D, the divergence of D, is nothing but how much volume is present inside the, how much charge is present inside the volume, that is volume charge density rho v. So del dot D is equal to rho v. This is also one kind of useful application. Now we are going to see similar concept of divergence we are going to use. Along with that, we will see the definition of, say this is our expression number 1. So this is, say this is equal to, we'll call it equation 1. Now we'll see the basic relation between electric field intensity and electric flux density. E and D, both of them are related with each other with one concept that is called as permittivity. What is permittivity? Permittivity is, we can say, it is the permission given by the medium to flow across it. So the relation between D and E is given by, say, D is equal to epsilon E. So this is our expression number 2. Now E, the basic definition of electric field intensity E is given by, this E is nothing but how much voltage is spread across the medium. So this E is nothing but equal to minus del dot V. This is nothing but del dot V. Now here we have to remember the difference. Del dot D is called as divergence. What is del dot D? Del dot D is called as divergence, because the definition is that if we take dot product of del with any vector, then we will call it as divergence. But voltage is a scalar quantity. If we take dot product of a scalar quantity, say voltage, then we will call it as gradient. So this term is called as gradient. Electric field intensity is nothing but the gradient of voltage. Voltage creates the electric field intensity. Because of voltage only electric field intensity flows. So say this is our E, say call it equation number 3 and keep it in equation number 2. So what we will get? We will get D is equal to minus of epsilon del dot V. Say we'll call it as equation number 4. Now let us keep equation number 4 in equation number 1. So what we will get? Let us put it. So let us keep the value. So del dot D, in place of D we will write del dot, we will get minus and epsilon del dot V is equal to rho V. In simplification, what we can write it? We can write it as, say, minus del square V is equal to rho V divided by epsilon. This expression is nothing but Poisson's equation. Now this is Poisson's equation, which says that the Laplacian of voltage is equal to rho V by epsilon. Now from the same equation, Poisson's equation, we can derive the Laplace equation. So what is Laplace equation? Laplace equation is applicable for the charge-free region. So Laplace equation, if you want to find out, so chargeless region means what? Chargeless region means where there are no charges, like air, space, the dielectric medium where charges are absent. So if we consider this expression number 5, in equation number 5 we have to keep the charges value as 0 so that we can get Laplace equation. So we will get del square V is equal to 0. This is nothing but Laplace equation. So I hope the continuity equation, Poisson's and Laplace equations are clear. These equations are used when some other parameters are not available in the given example. So we can find out volume charge density, and based on that we can find out other parameters also. So see you in the next session with new concept. Have a good day.